So I'm going to talk about I'm going to talk about design principle for building an anomaly detection system at very large scale. So these are the topics of what we'll talk about. While you read it, instead of me reading it, today I'm here with a T-shirt, and there is a reason for that, other than that it's our company's T-shirt. So a few months ago, I gave a talk in Berlin in a very nice old building that used to be a brewery, and I went there I'm used to conferences where you have to come with long sleeve shirts and because it's usually very cold. And it turns out that day was pretty hot in Berlin, and the building was a very old building with no AC, and the room was half of this size, but very, very stuffy. And about 10 minutes into the talk, I started sweating really, really badly. And it was a 40-minute talk. I actually cut it short to about 25 minutes because I just became completely wet. So today I came with a T-shirt to avoid that happening again, but it turns out here it's really cold. So if I cut the talk short, it's because I have to rush to the bathroom because this cold causes other issues. So now that you've all read what we're going to talk about, I'm going to start the talk and talk about anomaly detection. So why does anybody need anomaly detection? And besides being a nice unsupervised technique in the machine learning literature, there's really a lot of different areas and commercial areas where anomaly detection is very useful. If you look at web services that measure a lot of things about what they're doing and what the users are doing, basically anomalies can help detect business incidents and find unknown business opportunities and react to them. If you look at industrial IoT, which is becoming a very hot space, proactive maintenance of machines that you sell to your customer is really something that you need anomalies for if you want to be proactive about it. Security is an obvious one, detecting the unknowns attacks from data. So not everything can be encoded into rules, and a lot of things that hackers do are not, they haven't built the rules for them yet, so anomaly detection really helps there. Another area that I really like is machine learning. So we're designing a lot of machine learning algorithms. We're putting them in production, but they were trained on a lot of data that you collected. But who says that in the future they'll be still correct on the data that you see in production in the wild? So by applying anomaly detection techniques on the performance of machine learning algorithms in production, you can actually detect unknown things that you didn't know about and improve their performance as well. So that's, and there are several other use cases, but these are the ones that are the main ones, and applying it actually commercially saves time and saves a lot of money to companies. I'm going to focus a lot in the talk on cases that are really business incidents, because these are the main commercial things that, at least at Anodot, we do today, and I think are the main thing that are interesting. So how do you detect business incidents? Basically, detecting business incidents is using metrics, KPIs, key performance indicators. And key performance indicators can be at multiple levels, all the way from the top, from business KPIs, talking about revenue, number of purchases of products if you're an e-commerce site, the number of clicks on ads if you're an ad tech company, and so on. If you go one level down, you look at business opportunity-related KPIs, like how many users visited my site, how many people logged in. And you want to measure it, not just at a very high level, you want to measure it for every geography, for every browser that the users came from, for every page in your application, every device, and so on and so forth. So this is the second level. These are metrics that drive the revenues to your business. If you go one level down, you can look at more technical metrics, either from the application performance side or from the infrastructure side. And again, you want to see, do I have errors and latencies and usabilities for every class and feature and method that I have in my application, or every server and host or network infrastructure component that I have And you measure all of these metrics, and you end up, if you're a large enough companies, with millions to billions of these metrics. And companies such as, for example, Facebook, they publish that they have billions of metrics that they collect every minute, going all the way down from the infrastructure and all the way up to the business. And and a lot of companies understand collecting these metrics and looking at them is really the way to detect the performance of the business. So what do most companies do, and what do most people do for detecting these business incidents? In most cases, you see manual detection of business incidents using things like dashboards. Dashboards are very pretty, and you put up your key performance indicators, your key metrics, and you have people sit down and look at them. And when they look at them, they can visually detect that there are all sorts of weird behaviors in these KPIs, and those are these anomalies. So manually detecting, visually detecting anomalies is a very, very common way that people do it today. Now, of course, this is not scalable because dashboards can, I mean, how many graphs can you look at a dashboard yourself as one person? It doesn't scale because you need a lot of humans to look at all these graphs. And at the end of the day, you have dashboards showing your very high level metrics, but you might miss a lot of incidents at the lower level. Another technique is alerts, and alerts and a lot of systems allow you to put all sorts of static thresholds saying if my metric goes above a value or below a value, that's an incident, alert me on that. Now, that is great when you know these thresholds, and oftentimes you don't know these thresholds. Setting these thresholds on millions of these metrics can be very, very tedious, if not impossible. And there are cases where you absolutely cannot set thresholds. And you can see examples in the middle there where there's a drop in the middle that neither threshold actually captures. So, but when you think about it visually, with our eyes, we can easily see anomalies in these time series data. And so why not apply techniques that can capture those anomalies that we as humans can so easily find? So really the way that the world is going to is automated anomaly detection for detecting these business incidents. So what is anomaly detection? It's basically having a machine learn the normal patterns of your data and then detecting when it deviates from that normal pattern. And those usually give you very early warnings about things that are starting to go wrong because typically the normal behavior, deviating from normal behavior doesn't go off at once, but it starts very slowly. So see, these are some examples of deviations from normal. So the solid line is the actual measurements of number of visitors on a website, and this is real data. And you can see the orange part where it dips below the shaded area. That is an anomaly. There was an abnormal decrease in number of visitors compared to what it should have been at that point in time. And the shaded area around the graph, the baseline sleeve, the normal sleeve, is the expected value of that metric at each point in time. Here's another example. This is decrease in ad conversion on Android devices. And again, you see the shaded area where it should have been, and then it goes below it. And decrease in ad conversion actually leads to revenue loss. Some cases are not univariate. Some cases, to understand what's happening, you have to look at multiple of these metrics together. And this is an example of a price glitch where a website actually put up a product for a much cheaper price than it should have been. In this case, a gift card, instead of $200, publishing it for $15. So somebody can pay $15 and get a gift card worth $200. This happens a lot in airlines and hotels and e-commerce sites. And in those cases, usually what happens is the word spreads. A lot of people start buying it because, wow, it's free money, right? And then you see an increase in the number of purchases. But when you look at the revenue, which is the bottom graph, you see a decrease compared to what it should have been. So there's no actual decrease in the value, but compared to the forecasted value, it's a decrease. So looking at them in combination actually tells you, okay, there is an issue here, and it's probably a price glitch. So these are some example anomalies that are there in the wild and we see every day. So when I come to design an anomaly detection system, I have a few design principles depending on the problem I'm trying to solve. And there are a lot of different methods for doing anomaly detection and different use cases. So I'm going to touch a bit about the design consideration, and then later on I'll describe what we do at Anodot and why we do it that way. So there are four main design considerations. There are actually, there's more than just these four, but these are really the four main ones when you want to build a large-scale system. So first of all is timeliness. Do I need to get alerted on the anomalies really in real time? Or is it something that can happen retroactively? Is it something that I don't have to have beforehand? And I can, if you tell me that there was an anomaly a month ago, I can still do something with that. So that's timeliness. The second is scale. Do I have a system that creates hundreds of metrics or millions of metrics or billions of metrics? And that scale will dramatically change the type of methods I'm going to use for detecting anomalies. If I have just 5 metrics, I can use other methods compared to if I have 1 billion metrics. So that's the second one. Rate of change. So do I have a system? Am I measuring a system or a company? Or when I'm talking about a system, it doesn't have to be a physical system. Am I measuring a phenomena that constantly changes? Or is it something that is more static and well understood? For example, an airplane, measuring an airplane is something that is fairly static. The design of the airplane is not going to change after it's deployed for about 40 years, while e-commerce site is probably going to dynamically change all the time, and you're going to need a different type of algorithms to use it. The last one is conciseness. So I'm measuring a lot of different metrics that all describe the system or the world that I want to understand, that I want to detect anomalies in. Now, because I'm measuring so many things, if there is something that goes wrong, if there is an anomaly that happens, usually it affects many of these things that I measure. For example, if I'm measuring the human body, when I become sick and I have the flu, my heart rate goes up and my temperature and my perspiration is higher and my pH, skin pH is probably different. So there are a lot of different things that change, that change from their normal pattern. Now, when you show an anomaly to somebody, to a doctor, you want to show it all together so they can understand it and in a concise way, so that they can understand what all these symptoms mean. If you show them all separately, then it's very hard to understand what's happening. So these are the main design consideration. So let's double click on each one of these and see what they mean. So timeliness, real time versus retroactive. Some examples of when real time is appropriate and when non-real time is appropriate. So for example, if I see a reduction in number of visitors, when I have an e-commerce site or any web service and I see a reduction number of visitors in revenues, well, I need to know that fast because it could be because of a bug that's causing people to leave my site. If I see an increase in number of purchases of a particular product on my e-commerce site, then I should go and increase inventory today, not a month from now, because I'm going to run out of inventory and I'm going to lose money because people coming to buy that product are going to leave and go to another site. If I see an increase in ad conversion without an increase in number of impressions, usually that could be fraud. If I don't react to it right now and I don't have that in real time, then I'm losing money for that fraud. So I can't wait. So these are examples of real-time decision-making. While non-real-time decision-making that can afford kind of looking at history of anomalies and not having them run in real time, things related to planning. If I'm doing capacity planning, I want to see all the anomalies I had in the last 3 months so I can plan for the capacity in the future. Marketing budget allocations does not have to be real time. I can afford to wait, collect a lot of data and analyze it in non-real-time manner. Data cleaning, scheduled maintenance, anything that's related to these kind of things can be done in a non-real-time decision-making. Now, how does that affect what type of methods I'm going to use? So anything that's real-time decision-making, you typically need algorithms that are online and adaptive, so things that constantly learn from new data. You cannot afford to go back and iterate on top of your data. And that leads to a particular set of algorithms compared to non-real-time decision making. The disadvantage of online learning algorithms are typically that they're more prone to false positives because they cannot go back and fix what they have learned. But they usually scale more easily to a lot of data. The non-real-time decision-making techniques are batch learning techniques where you can go back and forth over the data and fix what you're doing, and it's easier to remove false positives these ways. But obviously, because you iterate over your data, it scales a lot poorly than compared to the online techniques. The second consideration that I mentioned is rate of change. Is my underlying world changing constantly or not? And that really affects dramatically what type of techniques I'm going to use. These are example, kind of more pretty intense examples of change. The one on the left, it's an actual metric from a real system from a real customer where it behaved in this seasonal pattern way, and all of a sudden changed its behavior, and it's okay. After it continued that behavior, and that was okay. So if you don't have an adaptive algorithm that knows how to adapt to these changes, then you're basically not going to be, at some point you're going to be completely useless as an anomaly detection system. Your model for what is normal is going to be useless. And this is the most common use case that, at least that we have seen. The other way, where things change very slowly or not change at all, those are usually closed systems like airplanes or machines that you built once and they hardly change or change very, very, very slowly. And then you can collect some data in the beginning for some period of time that you think is sufficient, learn from it what is normal, and then apply that model and not update it until the next release of Airbus plane or anything like that. So these are and obviously if you don't need to be adaptive, you can learn once and apply the model for a long, long time. The last point I wanted to mention is the conciseness of anomalies and how does that affect the method that you're going to use. So there are a lot of techniques and a lot of methods in the literature for univariate anomaly detection. That means you take a single signal metric, and you learn the normal behavior of that. And the examples that I showed you before are all those examples. There was one graph, one metric, and there was one normal behavior of that metric, and then you can easily detect deviations from normalcy for that metric. Now, these techniques are obviously easier to scale because if you are learning a normal model for each one of your signals by itself without looking at other signals at the same time, it's basically infinitely parallelizable. You can run it on millions and billions of metrics without any problem. All you have to do is add more machines, and it's very, very easy. Now, the issue with that is that when something wrong happens that affects more than one or two of these signals, and oftentimes it affects thousands of these signals if you have a large enough system or large enough world, then you're going to get an anomaly storm. You're going to get your system saying, oh, here are 1,000 of these signals. They're all anomalous, and you can't see the forest for the trees, right? Because there's so many things that shout at you, and you don't understand why you can't discern what is the actual root cause and what is the symptom from all these anomalies. They do have another advantage, which is actually quite important when you start dealing with large-scale systems and a lot of different types of metrics, is that it makes it easier to model the behavior of each metric and be more accurate about it. And you don't need a single model that fits all, and I'll show some examples of that later on. The other side of things is multivariate anomaly detection. It's a very, very powerful techniques that can use it. you learn a single model that describes the normal behavior using all the combinations of your metrics, all of them together. It can find very strange behaviors when one thing goes up a little bit and the other thing goes down a little bit, and it still finds that that behavior is anomalous without each individual one being anomalous. And it really gives you a concise picture of each incident. So whenever these models say there is an anomaly, they say there is an anomaly in this whole group of metrics, and their behavior together is abnormal. The issue with these methods that they're hard to scale, because again, you learn with a large set of features. So if you have 1,000 metrics, it's easy. But if you have 1 billion metrics, it starts to become hard because it's basically learning with a billion features. So you have to start running all sorts of techniques for dimensionality reduction and things of that sort. And it's still quite complex in terms of computation. It's also, in a lot of these models, hard to interpret the output. The output, there is an anomaly, but they don't necessarily give you an easy explanation of why they said there is an anomaly. When you look at each one of the metrics that you measured by itself, you might not see the anomaly. But so getting an interpretation of the anomaly is much harder in those cases. Lastly, if you have a heterogeneous set of metrics, meaning that they have all sorts of different weird behaviors, they're not all from the same distribution or even family of distributions, and they have all sorts of behaviors, then these techniques in practice tend to produce poor results. So if I want to measure network bandwidth for a lot of switches, and all I'm measuring is network bandwidth, for 1,000 or 1 million switches, that's homogeneous type of behavior. But if I'm measuring the number of visitors to a web page, and I'm measuring the memory consumption of a host, and I'm measuring the bandwidth, and I'm measuring number of errors of a method, each one may have a completely different behavioral pattern to it, and a lot of these techniques will not be able to combine them into a single model in a meaningful way, and will produce a lot of false positives. So there is a hybrid approach. This is an approach actually that we take at Anodot, which is to start with a univariate model, so learn the behavior of each one of these signals by itself, but then have a second step that looks at the anomalies in them and try to combine them into a meaningful group, a concise group that describes the anomaly together. So as a user, as a human, when you go to look at the anomaly and view it, you can see why there was an anomaly in each one of these signals, but then the group tells you the full story of the scope of the anomaly. And that lets you actually understand why the anomaly happened and react to it. So it's still scalable. There are challenges in terms of how do you know which metrics and which anomalies to combine together, because if I'm measuring 1 billion of these, by chance, by random, some of them may be anomalous at the same time. That doesn't mean they describe the same issue if I have a large enough system. So I'll talk about the challenges of how to know that metrics are related in this type of approach. So we talked a little bit about the design principle. Let's talk about a few of the anomaly detection methods out there. And obviously there are a lot, and this is not a complete story of all the things that can be there. But hopefully it will give you a taste of some of the methods. And I'm going to focus mostly on the online adaptive methods. So the general scheme of modeling, so the first step in anomaly detection is modeling the normal behavior, because it's an unsupervised technique, but you do assume that most of the time the signals that you're looking at are normal. Otherwise, anomalies are not anomalies. Anomalies are supposed to be rare. So the step one is to model the normal behavior of the metrics, of the signals that you have. And then the second step, devise a statistical test that tells you whenever given a new sample, does it fit the model that you trained or not? If it fits, it's not an anomaly. If it doesn't fit, then it's an anomaly. So you have to have a statistical test for doing it, and then you apply that test on each sample as data comes along. So this is very, very general, and obviously can be many, many methods to model the normal behavior. So how do you actually model the normal behavior? That is really where the magic happens. It's not that easy, and obviously, if it was easy, we would have a lot of people doing anomaly detection and implementing them in the wild. So some of the challenges in learning the normal behavior well are listed here. So the first one is, what is the type of signal that I have? How does it behave? And you have to classify them, and I'll show you some examples in a second. What is the signal distribution? So how does it have normal distribution or some other distribution, or maybe you don't want to use any type of known distribution to model it? And signals have all kinds of crazy distributions. Does the signal have seasonal pattern? This is something that comes up a lot, especially when you look at data from web services and anything that's human-driven. So any e-commerce site, anything that is driven by human, you see a lot of different types of seasonal patterns, periodic patterns, and you have to take them into account. And the question is, how do you take them into account, and how do you detect that they exist? The last one is, how do you adapt to changes? Because as we mentioned, we're looking most of the time at systems that constantly change, and you need your algorithm to adapt to those changes. So signal type and distribution. So here are some examples of signal types that lend to different types of distributions that would be required if you want to get a good normal model. And again, getting a normal model is easy. Getting a good one is the hard part. Because if you don't have a good one, you're going to get a lot of false positives or miss everything. So for example, you have most of the techniques out there in the literature talk about smooth or stationary signals. Signals that tend to be regularly sampled, and they have a stationary type behavior. But when you look at reality, you see a lot of different, and we look at millions of these metrics today in our system, you see a lot of different types of distributions, from metrics that don't get sampled regularly, which is okay. It's not missing at random, but it's missing because that's the behavior of what they're measuring. You get multimodal distributions, you get sparse metrics that tend to be a constant value and then all of a sudden spikes. And so, most of these spikes are not anomalies, they're completely normal. You have things that change as steps, you have things that have discrete values, and you have about 6 or 10 more that we have identified, at least from all the metrics that we collected. And I'm sure there are many, many more out there in the wild. So each one of them would require a different type of model to describe their normal behavior. So if you don't know, so there are two ways to overcome this. Either go over one by one all of your signals and classify them to the right model that they should fit, or design an algorithm that automatically classifies them to the right model and distribution that fits them. And really, without it, you're basically going to produce very, very poor models for normalcy. The second one that I wanted to mention specifically is seasonal patterns. Seasonal patterns happen all the time. This is a metric with a seasonal pattern, in this case, a daily seasonal pattern. It's a real metric. And if you don't account for that seasonal pattern in your normal behavior models, you might end up with a baseline sleeve saying that anything above that shaded area is abnormal and anything below it is abnormal. But obviously, that's not a good fit to that signal. If you do account for that seasonal pattern, then you can detect incidents, a real incident like that one over there on the right, where there was a abnormal drop compared to where it should have been for that time. So accounting for the seasonal pattern is really important. And this is a simple example, and a lot of methods use single seasonal pattern in them. But in the wild, you actually see all sorts of seasonal patterns. Oftentimes, you see multiple seasonal patterns, and this is an example of a weekly and a daily seasonal pattern of a real metric. So you can see that I call it amplitude modulation because you see that there is a convolution between the weekly pattern. It's like a sine wave, but it's more like a convolution between square wave at the weekly level. So the weekends are low, the weekdays are higher. And then you also see a daily seasonal pattern within a week. So not taking into account both of them in your normal behavior model would mean you're going to miss anomalies like these ones that happen either during the weekday or weekend, and so on. So if you want a good behavioral model for what is normal, take those into account. So this is another example. Here's another example of a seasonal pattern, but this one is 2 seasons. I think in this case it's 4 hours in a day, but in this case it's an additive seasonal pattern. Again, these are not made up examples, these are real examples from real customers, real data. So in this case, there is a daily seasonal pattern of going up and down, and then within the day, about every 4 hours, there is a peak, a square wave that lasts for a while and then goes down. And this is normal. This is okay, having that square wave. And if you don't take that into account, you're going to miss that anomaly in the middle there where it should have gone up, but it actually stayed flat and then even went down afterwards. So again, getting a good model of behavior, you have to take into account seasonal patterns and multiple seasonal patterns of all sorts: additive, multiplicative, convolutional, and so on. So I talked a lot about seasonality. How do you actually detect that there is a seasonal pattern? And there are many techniques, mainly from the signal processing world, and not necessarily the machine learning world, for detecting basically frequencies, main frequencies in data. So one of the most common one is finding maximums in the Fourier transform of your signal. And there are other techniques that use wavelet transforms that can find all sorts of seasonal patterns as well. The Fourier transform, the advantage of it is that it's relatively fast, n log n. The disadvantage of it is that it's very challenging to detect low frequency seasons, because you're going to need a very, very long sequence, and it's challenging to discover multiple seasons. There are all sorts of issues with computing the Fourier transform that cause all sorts of aliasing that make that challenging. It's also very, very sensitive. Well, I wouldn't say very, very, let's say sensitive to missing samples. So if you have a sequence of a signal and then it has all sorts of holes in it, it could really screw up the Fourier transform techniques that detect seasonality. There is another technique that is more robust to these gaps, which is autocorrelation techniques. And their disadvantage is that they're computationally expensive, they're n squared. And if you're going to compute that at large scale on billions of metrics, you're going to have a hard time doing it. And there is another technique that basically just creates some cost function of what is a season and exhaustively search for season. It's a lot more robust to gaps, but it is again challenging to discover multiple season. I could say from our experience, the best way is to use the autocorrelation of signals, but then you have to do a lot of tricks to make it fast if you really want to apply it on many, many metrics. So skipping to the next challenge is adapting to change. And here you need adaptive online algorithms. And these are just a few examples in the literature of adaptive online algorithms, from the simple moving average, which is probably the simplest one that you can think of. Just take a window and just move it and compute the average at every point in time, and compute the variance at every window, and then do a average plus or minus 3 standard deviation from that average. And then the length of the window is what determines how fast you learn. There are obviously a lot better techniques like double or triple exponential moving averages, Holt-Winters, single exponential forgetting, and even more advanced techniques, or there are superset techniques using ARIMA models or SARIMA models, seasonal ARIMA models with Kalman filter as the estimation of the parameters. And the literature actually has a lot more techniques than just these. Probably the most advanced are the SARIMA models. Now, all of these models have some parameters to them that say how fast do they learn? How fast am I adaptive? And how do you know how fast you should be adaptive? How do you know the rate of change that you should let your algorithms change the behavior based on the metrics? And that's actually pretty tough. So, and this is one of the main pitfalls. So if I let the algorithm adapt too slowly, let's take the moving average. If I make the window very, very large, that means I'm going to adapt very, very slowly to changes in my underlying signal. And I might end up with a very, very wide area of what is normal, very wide sleeve of that baseline. If I make the window too small, then I'm changing too fast, and then I'm going to miss a lot of anomalies. I'm going to think they're normal. So there is a trade-off between how fast to learn and how fast my underlying signal changes. So really the solution for that is to look at every one of your signals and auto-tune what's the adaptive rate. Assuming that most of the time there shouldn't be anomalies, you construct a cost function that will let you tune the parameters of your model that determine the rate of change of your signals. And then you get to the kind of al dente baseline that really fits your signal well, but still can detects the anomalies. Now, there is a pitfall there when you do the auto-tuning of the parameters, and and the reason is usually when you look at a signal and you do these auto-tuning techniques, they assume everything is normal, but you have anomalies there. Probably there are some anomalies, you just don't know where they are. So how do you adapt to it? And if you adapt too fast to anomalies, you might end up screwing up. So, just to give you kind of a high-level understanding of what I mean, so a few weeks ago I attended an event called Burning Man, and Burning Man is really 70,000 people coming together, and everything is an anomaly. Everything looks like this. So when you get there, you understand everything looks like an anomaly, and it is. But then if you stay there for a long enough time, and then you come back to the real world, and you come to Strata, all of a sudden everything here looks like an anomaly. So if you adapt too fast, if your adaptive rate is like a week, then when you come here, everybody here looks strange, because I'm used to seeing everybody naked running around on weird camel bikes and stuff like that. So if you take into account the anomalies when you're learning, you might end up thinking that the anomalies are normal, and then when it goes back to normal, you're going to think that everything else is an anomaly. So it's really tough. How do you do it? So the first strategy is to not do anything. Just take every sample, adapt with every sample as usual, and everything is fine. But that's probably not a good thing. So the way you probably want to do it is to actually adapt your learning rate when you detect anomalies. So again, you're doing adaptation of your learning rate. When you see anomalies, you slow down how you learn, the quickness of your learning, and when it goes back to normal, you can speed it up again to learn the new things. So this is an example of detecting a full anomaly and not detecting just the first samples of it. The last one I want to mention is anomaly conciseness, and here really what you want to learn, if you're learning each individual metric, you're going to want to learn the relationships between them, and so you can actually make a concise assumption. And this will be probably the topic of my next talk at Strata, because we're almost out of time. We use, at least in Anodot, two techniques to learn the behavior, to learn whether things are related to each other, whether two signals are related to each other, or millions of signals are related to each other. We look at whether they tend to be anomalous together, so abnormal base similarity, and we look at their normal behavior and also see whether they're similar. And out of that, we get a graph that describes the relationship between all the signals, and that lets us create very concise anomalies. And just I'll quickly go through the techniques here. They're basically clustering techniques, but if you want them to scale to billions and to millions and billions of metrics, you have to make them much faster. And here there is a technique called LSH, locality sensitive hashing, that lets you actually do this at large scale without very high computational cost. So let me just end with this slide, if I have last minute, just to give you a sense of the scale that we have at Anodot using the techniques that I mentioned. This is our architecture, and these are the number of metrics we consume today. At least I took the numbers from today in our dashboards. And really, the key takeaway from this architecture, if you're going to build a large-scale anomaly detection system, is one. Everything you learn needs to be online adaptive algorithms, and you better do that learning as you're ingesting the data and not after you store it in your data store. Once you store it in a database or Hadoop system or wherever you store your actual samples, you're never going to be able to scale your learning to all of your data. As the data is flowing in, let the algorithms learn the behavior, and update the models of what is normal all the time. And if you do that, and this is the middle part that we call Anodot daemon, it does all the learning in real time, then you can detect anomalies in real time, then you can scale up to millions of metrics, then you can, and you don't have to choose which metrics to run on. So with that, I'm going to finish, and I'll take any questions. Shameless slide showing customers.
So we have time for maybe one question.
Yeah.
You said you should look at heterogeneous when you look at multiple items. So the purchase versus revenue, is that in special case that's different because they are not the same?
Right. So it's really well. So I'm talking about heterogeneous mathematically speaking. So it could be that purchases versus revenue are kind of similarly behaving in terms of, in a statistical probabilistic sense. And then you can combine them into a single model. But oftentimes they don't. Oftentimes they have very, very different behavior. One may be very discrete and the other may be very smooth. And then trying to fit one model to both together is going to not behave well, because most models, let's say you apply PCA, that's a common technique to find anomalies. You apply PCA and you look at not at the main eigenvalues, but at the lowest eigenvalues, and the anomalies appear there. But PCA assumes that the variables that you put into it are first of all, continuous, right? Continuous valued, and then more or less normally distributed. And so if one of them is not, one of them is discrete, and the other is continuous, then PCA will produce a result, but it might be a very, very bad result.
All right. Thanks again, Ira.
Thank you.